I didn't get to talk about secrecy in the lecture we had last week about information and compression and error correction, so we'll start with that. So there is a way of communicating in public such that you can guarantee that no information gets known to anyone who you don't want to have the information. The way to do this, so first of all, it's pretty cool that you can do this. You can write on, say, on the sky with a jet, you know, and yet communicate something secretly to someone. And in order to do this and have it be provably secret, you have to have some sort of shared secret key between you and the person you're trying to communicate to that no one else knows. Okay, so let me show you how this can actually be done. So suppose we have, suppose before we wish to communicate, sometime like right now, we sit down, we flip a coin, make this big long binary sequence that we say this we're going to hold in reserve until some point in the future, maybe 10 years from now. We might be in different parts of the world, and then I will have something important I need to tell you. Of course, if I knew it already, I would just tell you while we're sitting in secret. Instead of exchanging a key, I would give you the message, but I don't have the message yet. Okay, and sometime in the future, we will use this key to send the message. All right, and what we're going to learn right now is the one-time pad. Okay, the one-time pad says this: it allows you to send a message that in binary is no longer than the length of your key. Okay, so if you have a key that's, let's say, 10 bits, and it's just a random sequence. Is that 10 bits? Yes. Okay. And you do not tell anyone this key, and then at some point in the future you have a meaningful message which you've converted to binary. All right, so the message, let's assume, is no longer than the length of your key. So this is something meaningful. Okay. The way you encode is you simply, bit by bit, do an exclusive OR operation. Okay. So you do XOR. In other words, a binary sum or a mod 2 sum. We record simply whether or not the two bits are equal or different. Okay. Different means 1 is written as 1. The same is written as 0. That's what an exclusive OR is. So this becomes a 1 because they're different. Go on to the next pair. That's a 0. The next pair, and so forth. Here, those are the same. So 0, different, 1, different, 1, same, same, different. Now I have a 10-bit sequence. It's just as long as my message originally was. Okay, and this I can write. You know, that's what I transmit. All right. Now we need to check two things. First of all, can we get the message back if we know the key? And secondly, if we don't know the key, have we really kept a secret? So let's first see that we can get the message back. Okay. So the other end of this communication scheme has this key. And notice that if you do the same operation, but you swap the place of the transmitted sequence and the message. In other words, you take your key, you take what you received, and you do a bitwise exclusive OR, you get back to the message. All right, so the exclusive OR of 0 and 1 is 1. 1 and 0 is 1, and so forth. You see that when we get, 1 and 0 is 1. And when we get to here, we get a 1 and 1. Those are the same, so we get a 0 and so forth. So the encoding and the decoding are exactly the same. All right, so yes, we did transmit the message. Now, have we leaked anything to someone who doesn't know the key? Have we leaked anything at all? Even if they can't get the information exactly, did they learn anything about our message? The length, oh good. Yeah, they did learn the length. So we would, if we wanted to hide that from them, we'd have to alter how, pad it with a bunch of nonsense or something. That's a good point. Okay, other than the length, did they learn anything? So they didn't, because what we can show is that the transmitted message here is independent of the actual message. All right. So probabilistically independent. And we talked about how independence meant, in particular, that the distribution function for the transmitted message given I put transfer for some reason. Let's say transmit. Transfit. Wow. Okay. The transmitted message given the actual message. Okay. If this is equal to just some constant that doesn't depend on the actual message, so it equals some distribution on transmit that's not a function of the message, then we have independence. Then we know that there's no connection here. Okay? And in fact, we can see that this part here is easy to evaluate because no matter what our message is, let's say the message bit here is a 1, but the key is random, right? So even though the message bit here is 1, let's say with not seeing a key, okay, you have no key here. Just because that's a 1, what's the probability that the transmit is a 1? That's what I need to do. Okay, what's the probability that the transmit is a 1 given that the message is a 1 and that the key is random? It's 50%. It's a half. What's the probability the transmit's a 1 if the message was 0? It's a half. So it didn't depend on the message. So you have this, which we know we can turn that around. Probability theory says we can turn that around and say that also means that the probability of the message itself, given the transmitted sequence, this is really what will be meaningful to us in terms of secrecy. So someone receives the transmitted message and the transmitted sequence, and they want to somehow reform their estimate of the message. And this is just going to equal the prior probability of the message, which was, may or may not be known, but didn't have anything to do with our communication. All right? So once we know that the top is equal, we know the bottom is equal too, and that's kind of the operational meaning. Yes, we want that whether or not they receive the transmission does not help them at all to understand our message. Okay, so this is a well-known scheme. And so we see that we could use this to communicate secretly. What are the downsides of this scheme? Using such a thing. Yes? Yes, so we didn't really emphasize this, but this key should never be reused because if someone learns about the key, they're going to indirectly learn about our message that we communicated. We should use this key and we should throw it away, purge it from our memory, never use it again so that no one gets a hold of it, which is why it's called a one-time pad. You might say, well, I'm going to reuse this key over and over. That's not going to be provably secret. Okay? And that will have problems. In fact, historically, that type of a thing has led to real wartime issues, that codes have been broken because people have reused keys. Yes? I think it's just kind of a description of this process that you just line them up and you do this sum. So what this means is the amount of message you communicate has to be smaller than the amount of secret key you have. You have to have some way of creating these keys. All right. Now, cryptography, modern cryptography, does not do this level of secrecy. If it did, we would have perfect secrecy. But it's considered infeasible in many situations to have that much key that you exchange. There are ways of doing this. So you can use, so you might say, well, how do I transmit the key? Well, I could load a CD full of random bits, get a bunch of hard drives, load them in a truck and ship them somewhere, and and have armed guards, making sure no one has read these, right? And it gets to the other end, and now we have a lot of key to use to send between 2 points. Okay. Now, couldn't I instead load my important messages into a truck and guard them and send them if it's the same amount of information? Well, there's one advantage to doing it with the key, and that is if some attackers come and get a hold of that truck in transit, they haven't actually learned anything yet. And all you have to do is be able to know that they did this. Okay? So you get the message back, they stole the truck. You don't use those keys, and you better figure out another way to set up a key. Whereas if you sent your actual information, then you're in trouble, right? So it sort of sets up sets up, it prepares a way to send information securely. Now, you can use a quantum channel to send random bits to a destination and know whether or not it's been intercepted. So quantum physics gives you a method of knowing whether or not it's been eavesdropped. It's sort of like this armored truck idea, but using physics to do it. And so those types of systems have been actually deployed. They can set up a fiber optic cable between some destinations that they can't be too far apart in current technology. So I'm not exactly sure. It's somewhere 10 to 100 kilometers distance. And you can then send photons and make sure that you've exchanged a key that you know no one has intercepted. And then you can communicate however you want using that key, and you know it's secure. Now, the way that modern cryptography works is they use actually very small keys. And technically, they're not using any true secret key. They use computation to set up keys that aren't really secret, but are believed to be secret from a computational point of view. So it's believed that in order for someone else to obtain your key, they would have to do an unreasonable amount of computation. Okay, so that's how actual encryption works that you use on the internet with money exchange and so forth. And it's been proven. So one of Shannon's first papers was about showing that this scheme, which was already known at the time, that it, of course, we know it's sufficient for obtaining perfect secrecy, but in fact, it's necessary. There's no way to use less key than the length of your message and have perfect secrecy. Okay, and you can use information theory to show that. So if you want perfect secrecy, this is what you're stuck with. Any other questions about this? So actually, it's similar in a way to quantum teleportation. If you've ever looked into quantum computing and the neat things you can do with physics, you can actually move objects. Well, you don't really. They say you're moving the object because you clone it in another place and destroy it at your local location, and you can do this if you have what are called entangled qubits. So if you somehow sent entangled bits between two destinations and they have these in reserve, that's sort of analogous to our key. Okay? Then you can, at some point in time, take a quantum object, put it in some quantum computer that operates on it with your entangled bits. Okay? And by the end, the other side, where they're also doing some processing with their entangled bits, your object ends up over there, and your bits are no longer useful. Your entangled bits are no longer useful. So it's actually sort of analogous. We're doing this with information, but you can actually do it with material in a quantum sense. Okay, so how about if we get back to linear time invariant systems? Okay, so let's talk about, let's revisit the system properties that we've talked about before, but assuming that the system is LTI. Okay, so we'll see some interesting things here. So let's say, what does it mean to be memoryless, causal, stable, which I will say bibostable, bounded input, bounded output. There are multiple notions of stable. This is what we're talking about. And invertible. Okay, so first, memoryless. If you know your system is LTI, and we additionally say it's memoryless, what can it be? What's that going to tell us about how the system behaves, its impulse response? Yes? Yes, it can only be amplification or attenuation. So Okay, so multiplication by constant. And so if we say, well, what does that mean about the impulse response? Let's put something here, impulse response. Okay, so h of t should be just some constant times delta of t. That would be the impulse response of an amplifier. We can arrive at that in two ways. The simplest way is to say, well, what does impulse response mean? Impulse response means the output of a system when you put a delta function in, right? So if it's just an amplifier, then you put a delta function in, out comes c times that delta function. Okay. Another way to see this is if we do look at the convolution of h with our input, and we want it to just scale the input, well, we know how to do convolution with a delta function. Convolution with a delta function is just the same thing as went in. Okay. So I guess we'll check that because I'm seeing a few blank stares. If it was discrete time, same thing, c times discrete time delta function. Okay, so these are the only memoryless time invariant processes. We can check that. We can say, let's look at h of t, x of t is our input, convolved with c delta of t. And that should equal, by linearity, c times x of t convolved with delta of t. And hopefully you recall, or you can check, that x of t convolved with delta of t is just x of t. So there we go. If it has this impulse response, it will scale. The important thing is this is the only memoryless LTI system. Okay, this will make more sense, I think, as we talk about causal. Okay, so if an LTI system, not memoryless anymore, but it's causal, what can we say about its either the frequency response or the impulse response or something? What does that tell us about it? I mean, we know the definition of causal, but it's going to tell us something even simpler for LTI systems. Yes? Perfect. Okay, so h of t equals 0 for all t less than or equal to 0. Less than 0, let's just say. Not less than or equal. Less than 0. Okay, same with discrete time, same thing. Okay, a picture will help here. We have t, we have 0, and we have an impulse response. Now remember, for an LTI system, impulse response tells you everything about this system. It's very nice because for a general system that wasn't LTI, you have to have some description that tells you how every input is handled by this system. Okay, imagine trying to describe Windows operating system, and say how is it going to handle every possible input? I guess you'd have to give all the source code, right? Okay. On the other hand, if it's LTI, to say how it handles every input, all you have to give is an impulse response. Okay, because we know all it can do is convolution, right? Okay, so what we have here is that so what we have is that the impulse response can look like this, whatever it wants, on the positive t side, but on the negative t side it has to be 0. Now, maybe you should ask some questions because I find that many people find this counterintuitive when they first hear it. Why is this a causal system? So, yes? Yes, that's a good way to think about it. So convolution flips the function, right? And so because you're thinking causal means inputs only affect the future of the output, right? Or conversely, it means that outputs are only affected by the past of the input. And yet this is saying something about time being positive, and that gets confusing maybe a little bit. But you have to realize what an impulse, how to interpret an impulse response. So it was just stated that you could think about this as convolution x convolved with h equals, as we know, it's an integral of x of tau h of t minus tau t tau. Okay? And so we see that for any point in time t, if we have this property here, right, that is 0 for all negative t, then what we get is that for any point in time t here, then this is 0 for all tau that are greater than t, right? So because we flip, this sort of flips h around. So it's saying for all tau after the point t, this is 0, therefore this result of this integral is not affected by anything in the input that happens after time t. Okay? So actually, a good way to think about the impulse response is that it's telling you how much the output depends on the input at a certain duration in the past. Okay? So this impulse response you can think of as saying, well, the output at any point in time is some sort of weighted average of the input centered around that point in time. Okay? But the impulse response tells you exactly how much it depends on each point in time. So it says, well, the impulse response at time 0 is saying, well, it depends this much on the current value of the input. Okay? And as we go over here, if this was at time t equaled 3 of the impulse response, it's saying the output depends to this degree on things that happened 3 seconds ago, 3 units of time ago. And if we go to 5 and we get the value at 5, we say it also depends to this degree on the input 5 units of time ago, and so forth. So that's how you should interpret an impulse response. Because remember, the impulse response is just saying what came out when you put a delta function in, and this is what came out. So if it's small, then it no longer is affected much by the delta function that came in that amount of time ago. Okay? So this is your weighting average function, but positive t in the impulse response is really saying how long ago of the input. You're depending on that input a certain amount of time ago, and this is how much you depend on it. Okay. So we have causal. These are all if and only if. I mean, it's only causal if this is true, and it is causal if this is true. Right. All right. So how about stable? Now this is a little harder. Any guesses on how you can tell if a system is stable by looking at, say, their impulse response or their frequency response? By looking at the impulse response either in time or frequency, can we tell? Well, remember, what is by both stable? What does it mean technically? What's the definition? Yeah? Yes. Yes. Good. You would think that that's the case. That so you said that you could check by frequency response being finite. Because it's okay to amplify things and be stable in this definition, as long as you don't amplify it arbitrarily, right? There just has to be some constant where you can say if the input's in this small window, then the output is in some other big window, right? Funny thing is, it's actually hard to find anything in the frequency domain that immediately tells you if it's stable, because I can give you an impulse response whose Fourier transform is bounded, and yet it's unstable. in fact, you'd be surprised that the simplest frequency response we've looked at all course is not actually bounded, is not actually bibostable. What do you think I'm referring to? The what? Okay, delta function definitely also would not be stable, but there's another one, the low-pass filter, the ideal low-pass filter. Okay. The rect function in the frequency domain, exactly. Okay, so that's bounded, right? It looks totally benign. I mean, you say, oh, all the low-pass filter. Let's look at this example of unstable. So this can be very surprising. Let's say in the frequency domain, meaning here's h of f, and let's just have it be rect. Okay, of height 1. Okay. Believe it or not, this is an unstable system under this definition. And to show that it's unstable, I should give you an input that makes the output blow up. All right. Turns out, if I let the input be what looks like a square wave, meaning something that just goes like this, centered at 0. Okay, so 1, minus 1, 1, minus 1. Okay, and I have to pick the frequency just right. Okay, in fact, in this case, I want the frequency to exactly be a half. So, yeah. So, and then what I'm going to do is, let's say, frequency half of this square wave. And then I'm going to, at some point, I'll do this for a long time, infinite time, if I want just an example, but do this for a long time, and then let one of these be double in width. And then just continue on again, as if nothing happened. Okay? Now, this is a bounded input. But you will see that as you stick this into a low-pass filter, the output centered around this point here where I did this is going to just be huge. In fact, it'll be infinite if I did this for infinite width. Okay, it'll be as high as I want to make it, depending on how long I stretch this square wave out. Okay, why is that happening? Well, there's actually an easier way to check if something's bibostable. Yeah, go ahead. Exactly, the y value, the amplitude has to be bounded. Yes, that's what we're meaning by this definition of stable. The amplitude has to be bounded, and it's not here with the ideal low-pass filter. Okay, so let's see. You'll see why this happens in a moment. So what is the time domain of this? What's h of t in this unstable case? What's h of t? It's the sink. Right? So it's actually easier to check for stability in the time domain here. All right? So sink looks like this. All right? That's 1, 2, height of 1. Okay. Now, when we do the convolution with this input, we do a flip and a shift and an inner product. Okay, so I'm claiming that at time 0, let's say this is centered at time 0. This here is time 0, so it's symmetric. Okay, t equals 0. Then I'm saying the output, if you put this input into your system, the output is going to be infinity. Okay, well, how do we check that? Well, we do if we flip this, it's symmetric, right? And if we shift, how much should we shift? Because I want to calculate the output of the convolution at time 0. So to calculate the output of a convolution, we shift to the point. We shift by the amount of time of the output. I want to calculate it at time t equals 0, so I don't shift. So I flip, which doesn't change anything, and I don't shift. So really, all I'm checking is what's the inner product between this and this. Okay. Okay. Now notice what I've done here is I'm going to overlay that signal. It would be more interesting if I did it up, but oh well, doesn't matter. Okay, I'm going to overlay it like this here. And I've timed it just right. So it's always doing this type of thing. So when I multiply these, what do I get? I get something that's always positive. What? Exactly, I get. So multiply, and I get absolute value of sinc t. Something's always positive, right? Okay, now I'm going to integrate because it's an inner product. Do you think you can integrate the absolute value of sinc and get a finite number? You can't. Think about sinc as something, the top is pretty benign. It's just a periodic thing, right? Pi t over pi t. But the denominator only goes, there's a first order fall off. So integrating this would be like summing the harmonic series, summing 1 over n, from n equals 0 to infinity or something like that, or 1 to infinity. And that does not converge. Okay, so this integral is infinite, and remember, it's the integral we were trying to calculate. Convolution does an integral, right? Okay, so what we would get here, if we did this convolution, we'd get something that also at time 0 just goes bleep, really huge. All right, go ahead. What's your question? Well, because I'm looking at the, yes, so I'm doing a convolution. Here we have it written out, right? Which means it's a flip and a shift, a multiply and an integrate, right? So the flip and the shift didn't change anything here in either case, because I'm only calculating the output at time t equals 0. Normally when we do a convolution, we calculate the output at all time, right? The result of convolution is a signal in time. And so we would have to consider all shifts. But I'm only trying to look to show that there is a point in time where this is unbounded. Okay. Can anyone think of a way of then checking whether a system is stable? Yes? Okay. So you're saying stable equals, okay, h of tau, t tau. Okay, and this we would say, this is called being absolutely integrable. Absolutely integrable. Okay, so if the impulse response is absolutely integrable, then there's a claim that maybe the system is stable. In fact, this is if and only if. Yes, this is what it takes to be bibostable for an LTI system. So the if part is easy because all we have to do is say, well, I'm not going to write this proof out formally, but it's really quite simple. If we want to show that if this is true, and we then want to claim that that it's bibostable, all we have to claim is that all we have to do is say the input is bounded between plus or minus b, right? I guess I will write it. Assume this. Okay. Then and assume that the input x of t is in absolute value is less than or equal to some b, right? There's some bound on it for all t. Then what we want is show let's look at the output. Y of t equals x convolved with h of t. All right, and we want to show that y is also bounded. So then the absolute value of y of t, we want to show this is less than something. Well, that equals the absolute value of this integral I'm just writing the convolution integral here. X of tau, h of... I'm going to write it in reverse order just so I don't have to... So it's less confusing. Remember, convolution commutes. X of t minus tau, d tau, absolute value, right? Now, you can bound... if you move the absolute value within the integral, you get an upper bound. Okay, so turns out that's less than this. And, of course, multiplying two things and taking the absolute value is the same as taking the absolute value of each one and multiplying. So that equals absolute value of h of tau, absolute value of x of t minus tau, and now we're basically done because the second one is bounded by b. b d tau, which is equals b times whatever this number was. So let me say, assume that is less than infinity. Right? That's what we're saying. Assume that's less than infinity. Then we just get b times whatever that number is our new bound. So done. It is stable. Okay. Now, to prove that you need this in order to be stable, all you have to do is say, let's just generalize my example here for the unstable system. Suppose that the absolute value is not absolutely integrable. Let me put in an input that is just the sine of h. That by sine, I don't mean sinusoid. I mean it's a 1 if h is positive and a negative 1 if h is negative. Sorry, okay. My example is flipped upside down. All right. It's a negative absolute value of sinc. Does not change. So we get a negative infinity. Okay. Sorry about that, but it's still a counterexample. It would have been nice if I would have made the long part at the top. Okay. But it doesn't matter. So in this example, the blip that comes out is negative infinity. It still works to show that it's not stable. Okay. But what I can do is I can let my input be the time reversal of of a function that's always, there's 1 whenever the impulse response is positive and negative 1 whenever it's negative. This is a bounded function. Okay? And when I do the convolution, I'm always going to get the absolute value of the impulse response that I have to integrate. Okay. So in other words, this counterexample can be generalized. If anything does not integrate, if it integrates to infinity here, then I can always show that it's unstable. Okay. So that's exactly the condition. All right. Questions about this? Yes? Yes, that will still hold. Yes, so even if h is complex valued and x is complex valued, this will still be the condition. And the proving that it's stable would follow these same steps. But then I guess to construct the counterexample for unstable systems, you'd do more than using a sine function. You'd undo the phase, make sure they all add up. Yep. Good point. Okay, so invertible. Okay, now, how can you tell if an LTI system is invertible? Well, let's talk about this for a minute. I think what I want to do here is kind of go into some examples of inverses of systems. But I think some of you know the answer, so I'll field some answers first. Well, what does it mean to be invertible? It means if f and g are inverse systems, then that means that if you put x of t in to f, something comes out and you feed that into g, then you get x of t back out. That's what we're really looking for. You could do it in any order. Okay. So when it's if it's LTI, we know that for LTI systems, we know in the frequency domain, the LTI system is easier to understand when it comes to operating on systems. Okay, so in general, we know that out here we have an x of f coming into an LTI system. Let's say this LTI system has an impulse response f of t. It's a convolution with f of t, and there's a convolution with g of t. Okay, then we get that times f of f times g of f. Okay, this would be the result in the frequency domain of applying an input to an LTI system. There's the Fourier transform of that LTI system. And then the result of this together goes to the input of the next system. So you get another multiplication by g of f. And what we're saying is this should equal, you should get back to x of f if it's invertible, right? Therefore, if these are inverses of each other, therefore f equals f times g equals 1, or let's say g of f equals 1 over the first system for all f. Okay, so if g is the inverse of f, then in the frequency domain, it's literally the normal inverse we think about with fractions, right? It's 1 over the Fourier transform of the original system. Okay, so this leads to, we'll have some interesting discussions now about about what this does. Okay. Well, can you tell me first what would make, so I'm saying that not all LTI systems have an inverse. How could they not? I just showed you how to calculate the inverse. Yes? Yes. So if this Fourier transform is 0, some f, then there's no inverse, right? Okay. Now, I want to get to a discussion about filtering today, and so I'll talk about this as a filter right now. So what if we consider magnitude and phase? Phase of these systems, okay? So, in other words, this first system, F, has a magnitude and a phase. And often, when we look at systems in the frequency domain, we separate that, we represent them with these two parts, right? Because they're complex numbers. They need to be, if you're going to graph them, for example, you need to graph them in 2 dimensions. So magnitude and phase is a common way to do it. So what we're saying is you have something like this. If you have something like this, then it's not invertible. And it's very intuitive to understand why it's not invertible. So here's the phase, let's put just for completeness. And the phase really does not matter for deciding whether it's invertible, because we can tell whether it equals 0 by looking at the magnitude. And you see here, information is lost here. So when we say information is lost, I say if you put x of t into this system, whatever frequency information was in that range vanishes. There's no way to recover that. Therefore, the system is not invertible. Okay. Now, there's another type of not invertible where you're just missing isolated points. That still technically would make it not invertible. But in practice, that's not always as bad of a situation. You can almost invert it. Here, what we find is if you have a whole region where you have 0, then there's no hope to recover a substantial part of your signal. Maybe your whole signal lives in just that frequency range, okay, and you can't recover it. Okay, so what if, so this one is not invertible. Now let me do one that is invertible. So here we have some, let's say we have something like this. In magnitude. And let's say the phase is like I drew above here. We'll do it like this. You might notice in my pictures I'm always drawing the magnitude as even and the phase as odd. That's because if the system is real, that will always be true. Okay. Now, say that that's a height of 1. Can someone suggest, actually, is someone daring enough to come draw what G, the inverse, will look like based on magnitude and phase? So I've given you F here. I'm wondering if you are able to do this computation at least conceptually, do this inverse in magnitude and phase. Okay, yes? Come on, you can come up here and draw it. I'll give you your plots. Okay. By the way, when you use this pen, it's okay to rest your hand on here. It won't bother it. Okay, so go ahead. Oh, you might be pushing the little button. Excellent. And what did you do? Can you explain why you drew this? I'll put a little 1 right here.
Phase was easy because the phase just have to add up to 0. And magnitude, I decided to make the part that ends up being steady 1 because it doesn't really matter because you can scale it.
Okay.
And then
let me do that.
The downward peaks are like half of 1, so they go to 2.
Whoops.
Scale up a bunch. But the big up peak is maybe only 3 halves, so it goes to 2/3, which is pretty close to 1.
Okay. So what you said there is that the magnitude, what you said something important. The phases add up to 0. Okay. So what I want to emphasize here is that when you multiply two things, remember we've got F times G equals 1. Okay, these are two complex numbers. I want to drive home the point that that the magnitude of a product of numbers is just the product of the magnitudes. Okay? And that the phase of a product of numbers, in this case it's functions, but for each f they're just two complex numbers, is the sum of the phases. this is important to understand how things affect each other in the frequency domain, because we have complex number in the frequency domain. We have multiplications of complex functions whenever we're dealing with LTI systems. Okay, and you need to be able to recognize what happens to the magnitudes and phases. So when you multiply, you're just multiplying the two magnitudes. So what she did here was she wanted the magnitudes to multiply to 1. So she just took an actual inverse of these functions as real valued functions, right? And the phases you want to sum to 0, because in the end, we're trying to make the product equal 1 with 0 phase, right? So therefore, they have to be negative of each other. Okay, so it's important to realize that this same computation happens whenever you convolve two things. And for example, if you have, so filtering is really designing LTI systems to have a certain frequency response, to behave a certain way in the frequency domain. Usually you design it for its frequency domain behavior. So what that means is you're designing h of t, and we have h of f, which is the Fourier transform of what we design. We call this a number of things. You've heard me today call it frequency response many times. Sometimes it's called the transfer function of a system. And the point is that once we have h of f, then we know that if we also look at the Fourier transform of the input to the system, we know that it's just going to interact with the Fourier transform via a multiplication. Therefore, if we put x of t into our system, then we know that the magnitude of y of f, right, is going to equal just the products of the magnitudes. And the phase of y of f is going to equal the sum of the phases. Okay. So I have some examples of filtering, but I first want to talk about a particular LTI system here, or a particular system. Okay, so what if we have a differentiator? X of t comes in, and for any input, what comes out, let's assume the input is differentiable, what comes out is the derivative of x. All right. Is this system linear and time invariant? Let's address both of them separately. Is it linear? Well, it is linear, because we know that if we have ax1 of t plus bx2 of t, and we take the derivative, that just equals ax1 prime of t plus bx2 prime of t. Okay, and that's just saying take the derivative of each separately, then combine them. So yes, it's linear. And it's time invariant as well. Because if we said, let's take the derivative of x of t minus cap t, okay, take that derivative, in other words, put that into our system, then we know how to use the chain rule for derivatives. We take, it's going to be x prime of t minus cap t times the derivative d dt of t minus cap t, which is just 1, right? So it's just this here. Therefore, shifting beforehand and taking a derivative is the same as taking derivative and then shifting. Okay, so this is LTI. Okay, so here's another couple systems. What if we have an integrator and so out comes the integral from negative infinity to t of x of tau d tau. Okay, I'm going to give you a couple different systems to think about. Very similar one here, where out comes the integral from 0 to t of x of tau d tau. And so why don't we answer, are these two, integrator 1, integrator 2? Is integrator 1 LTI? Okay, so this, yes, it is an LTI system. We can check it just like we checked the previous one. Is integrator 2 an LTI system? No. What's breaking for system 2, making it not linear time invariant? So the actually the linear works, right? It's still linear, but the time invariance no longer works. Not time invariant. Okay, we can check that. Put in something like if x of t is a rect of, let's say, t minus a half. So that means it's like this, 0 to 1, right? Okay, if you put that into this system, what is the output? Say this is integrator 1. Let's say this is integrator 2, right? We're trying to show that integrator 2 is not time invariant. Okay, so then what we get out is the integral of this, for each t, we get the integral of this thing from 0 to that t. Okay, so we can see that, well, for every t negative, it's just 0. So we get like this, right? And for t positive, at first you start going up at a slope 1 until t exceeds here, and then it's flat again, right? So that's the output. All right. Now let's shift the input. Let's look at x of t equals rect t plus a half. So all I've done here is shift it like this. And again, let's apply this integrator 2. And we get that now if we do the calculation, for all positive t, it's 0. And for negative values of t, we start to get an integral. It's an integral from 0 to t, but t is negative, so it's going to be negative of the switched direction of the integral. So it's going to go like this. Okay, and clearly that's not time invariant because shifting the input here did not result in the output just shifting. Okay, so really the reason this type of integrator is not LTI is that 0 sitting there. Okay, it kind of gives you an absolute reference frame. The system, time 0 actually matters to this system. If it's linear time invariant, it should not, absolute time should not matter. Okay, but this one's fine. LTI. So let's go back and visit these two LTI systems. Say, what is the impulse response of this system? H of t equals what in both cases? So what's the impulse response up here? Well, let's do this bottom one first. That'll be easier. What's the impulse response down here? To find the impulse response, you just put a delta function into this thing. and calculate what comes out. Yes? It's just one, almost 1. It depends on what t is, because remember, you're right, it's 1 if the delta function's within the limits of the integration. So as you go along integrating, if you haven't reached, the delta function occurs at time 0. If you haven't reached time 0 yet, it's 0. But once you get past time 0, it's 1. Yes, so it's actually u of t. We have a name for that function, right? That's 1 for positive t, for non-negative t, right? Okay. So interesting that if the unit step function is the impulse response, then it's this integrator. All right. Now, what about up here? Well, if we put the delta function in and it takes a derivative, now we have delta prime of t. Delta function was already made up and mysterious. And now we're going to invent a new function, delta prime. In fact, people have fun with these and do second derivatives and third derivatives. So I'm going to give you a few rules for delta prime. They're just kind of the obvious rule. If you want, you can think of delta prime just like we constructed delta. Delta was a very narrow rectangle function, right? Okay, now we need to differentiate this. Well, yes. In fact, instead of a very narrow rectangle, if we treat delta like, if we let delta of t, it would be equally good to make it a very narrow triangle function. Okay, we could have constructed delta that way. And therefore, delta prime of t is going to be something very big and then something very small. Something like that, but in the extreme. Okay. In fact, if delta function, for the delta function itself, the height had to be the inverse of the width, right, to keep the area 1. For this, the height is actually going to be much bigger than the inverse of the width, if you think about it, because think about what this slope would be. The height is going to be the inverse of the width squared, basically. Okay. Anyway, so you can think of a delta prime this way if you want. I'm only introducing it here because, well, you'll see it here and there throughout your lives, so you might as well have seen it. But also, we can give some rules. Just like we have rules for the delta function under the integral, we have the rule for delta prime. Let's let integral of delta prime of t, f of t. In fact, we'll do delta, just like we have the shifting property, let's let this be generally t minus cap t, f of t. So think of this as a derivative of a delta function occurring at cap t. And this is always going to equal f prime of cap t. All right. Okay. So that's the rule, assuming f was differentiable at that point in time. Okay, so we have this. Anyway, we knew this is linear time invariant, and so we should have some impulse response, and now we do. It's a delta prime. All right. Now, one thing is kind of nice here. What do we know about the relationship between this differentiator and this integrator? These are inverse systems. If you put one after the other, you get back to the original thing. Okay, so let's use that knowledge. Let's look at the frequency response of the differentiator. Okay. So we want the Fourier transform of delta prime of t. Well, good news, because we have a rule now for how to use delta prime. So let's just plug that in. Integral of delta prime of t, e to the minus I, 2 pi f t dt. Okay, and we know that should be just the integral, the derivative of this evaluated at t equals 0. So the integral of this evaluated at t equals 0. All right. sorry, I said integral, but the derivative of this, evaluate at t equals 0. What's the derivative of this with respect to t? And now we plug in 0. Okay. And so we see that it's just minus I 2 pi f. So this is kind of fun. That is the frequency response of a differentiator. So the derivative, you can think of, now that we know that it's LTI, you can think of it as just some sort of filter. I mean, it's just going to either amplify or attenuate certain frequencies of your signal. So let's plot this thing. So this is, I'm going to give it a name. I'm going to say d of f for differentiator. So d of f equals minus I 2 pi f. Okay. So what is the magnitude of d of f? Well, how do we calculate a magnitude? Well, it's going to be too obvious to some people that it's, but we'll go through and calculate it using the fact that it's square root of d of f d conjugate of f. I'm only doing this so you realize that you can find magnitudes of even more complicated functions. Okay, this one's very easy. So that means it's minus I 2 pi f. And what's the conjugate of negative I 2 pi f? Okay, equals, and we simply get square root of 2 pi f squared. The I and negative I become 1. 2 pi f. And that we could have got just by inspection from here. Okay. And what is the phase? This we will do by inspection here. D of f. What is the phase of this thing? Well, this is a purely imaginary negative number. So the phase is negative pi over 2, right? However, that's only if f is positive. If f is negative, well, then it's a positive imaginary number, right? So that it's pi over 2. Okay, so the plot of this thing, the differentiator, is the following. We have that the magnitude is just like this. It's just linear with slope 2 pi. Oh, whoops, I should say absolute value here. Yeah. So when you square something and take a square root, we get positive numbers. So. All right. All right. And the phase is just like this. It's negative here. This is pi over 2, minus pi over 2, and pi over 2. So there is our magnitude and phase of the differentiator. So it's now, if you were going to describe this, yes, go ahead. Oh, yes, this one. Thank you. Okay, is there more questions? No. Yeah. Sure. For f equals 0, it's because the magnitude's 0, then phase is whatever we want it to be, I guess. So that does bring us a good point, which we'll mention in momentarily here. But so this is interesting because a differentiator you can think of now as a filter, if we want, with this frequency response. It's somewhat of a high-pass filter. It passes everything, but it amplifies higher frequencies more than lower frequencies. That's all it does. Okay. Now, then, what if we wanted to know what is the... let I of f be the transfer function for the integrator. So indirectly here, what we're going to do is we're going to calculate we know the integrator has this impulse response, u of t. Now, if you try to calculate the Fourier transform of u of t directly using the integral, you're going to have problems. Okay. We're going to get at it indirectly by realizing that these are inverse systems. Right? So the Fourier transforms of these two things must multiply to 1. So that makes it very easy to figure out what the Fourier transform of u of t is. So we know that in magnitude and in phase, I of f must be the inverse of this. It must look like the following. Must amplify low frequencies, right? And the phase should be the flip of this. Okay, and there's one catch, though. Is the differentiator actually invertible? According to we talked about LTI systems and whether or not they're invertible. And why do you say it's not invertible? Because we have a 0 here, right? And we said if there's a spot in the Fourier transform that's 0, we can't invert it there. Okay, and that actually becomes meaningful in this case because the Fourier transform of the integrator is not just this. It's ambiguous at time 0, and in fact, it has a delta function right here. So if you look it up in a table, you'll see it's this plus a delta function is the Fourier transform of the unit step. Okay. Now, what does it mean that the differentiator is not actually invertible? I mean, in reality, can you undo differentiation? What can't you undo? Yeah, you can't undo constants, right? So if I put x of t into the differentiator, or if I put x of t plus c, x of t as a signal plus a constant c, the same thing comes out in both cases. So there is ambiguity when you take a derivative. There's ambiguity on what went in. And that's exactly what we're seeing here. We're seeing that the ambiguity happens at frequency 0. What signals have frequency 0? Yeah, DC signals, constants. So it's saying you do lose the DC part. You lose the constant when you take a derivative. And that's why when you try to undo it, you have ambiguity here. Okay. Well, we're out of time, so we'll stop there.